When you multiply two complex numbers, it works very similarly to the way that you would multiply a monomial times a binomial or two binomials. However, one very important thing to remember is that whenever you see an I squared, by definition, that always equals -1. So for example, if you wanted to perform this multiplication, what you have to do is distribute. Okay? So you do 2i times 3, which is 6i, and then 2i times -12i, which is -24i squared. But you have to remember that I squared equals -1, so this is the same thing as 6i minus 24 times -1, which makes that 6i plus 24. Well, because this is a complex number, we should write it in standard form, which has the I in the back, so 24 plus 6i. Okay, and let me just squish this a smidge so it'll fit. Okay. So similarly, if I wanted to perform this multiplication, I just need to distribute the I, so it's equal to I plus 2I squared. Well, I squared, remember, is -1, so this is the same thing as I minus 2, and we should write this in standard form as -2 plus I. Okay. Now it gets a little more complicated when you have two complex numbers that have both real and imaginary parts. Now you just multiply these as if you would multiply two binomials. You can use either FOIL or you can use the box method. So some students prefer the box method because it's a little more visual. I'll do this first one using that method. So what you do is you draw a box and you write the two complex numbers above and to the side, and then where the row and the column intersect, you perform that multiplication. So in this one we would do 1 times 2, which is 2, and then this one would be 4i, 3i, and then 6. Let me write this a little smaller. 6i squared, but remember I squared equals -1, so this is -6. Now the reason a lot of students like this box method is because notice that the ones that are across from each other are like terms. Okay? These are the real parts and these are the imaginary parts, and as long as your two complex numbers are in standard form, it'll always be that way, where these two boxes are real and these two boxes are imaginary. So all you have to do is add these two here, which is 2 minus 6, so that equals -4. Okay? And then 3i plus 4i is 7i. So this adds to -4 plus 7i. So if you use the box method, it'll always be this way, where this one's real, this one's real, this one's imaginary, this one's imaginary. Okay? Now you can also use FOIL, which means you multiply the first, which is 2, then the outside, which is 4i, then the inside, which is -i, and then the last, which is -2i squared. Now I recommend, if you notice that there's an I squared in it, not trying to go ahead and convert it here. Write it in the next step, because then students will kind of make some sign errors, so it's best just to write the I squared and then change it to the -1 in the next line. So this would be 2 plus 4i minus I. Since this is -1, that makes that +2. So this is equal to 4 plus 3i. Let's try the last one, and I'll do this one using FOIL. So first is 16, then outside is plus 20i, then inside is minus 20i, and then last is -25i squared. So let's rewrite this I squared. So it's 16 plus 20i minus 20i plus 25. Well, now notice the two terms in the middle. The two imaginary parts cancel each other out, leaving me with just 16 plus 25, which is 31. I'm sorry. 41. Okay. Now these two numbers, because they are almost the exact same except the imaginary parts are opposite of each other, are what are known as complex conjugates. Now complex conjugates, whenever you multiply them, they will always follow the following form, where notice the two imaginary parts canceled out and then the last piece became positive, okay, and it became real. So what it ends up being is the real part squared plus, and it's always plus, the imaginary part squared. Okay, so you could just use this formula to perform this multiplication here. This works similarly to the difference of two squares formula, or multiplying the sum and difference of two binomials. Except instead of this being a minus, it is a plus when you're talking about complex numbers.